analysis. So what? Sorry. Okay, so right. So while you're launching that, it should be quick. But just a quick recap what the cluster-based permutation analysis was. And so this is the analysis to test when you want. Oh, sorry, this analysis you can use when you want to test whether two conditions differ in a specified time window. Okay, I'll share my screen. Showing these. Right.
Is he in?
Right, I think you can see this. Right. Anybody still trying to open the tutorial? Very good to go.
Yeah, I think we're good. Yeah.
Okay. Right, then I started with a setup. So the tutorial always starts with a setup page. So this is the packages that you need to upload it to run this tutorial. But I think if you are able to open the tutorial, that means you already have these packages loaded. So everything's good. For this analysis, we are using two packages, Exchange R and the cluster form package. But as I note, some of the functions in these packages currently don't work. So we will do another method for today. But yeah, I'll explain that later. So that was the setup. This is the same setup as yesterday. So if you want to see the numbers in this format instead of this format, you can run this to do so. Okay, then let's look at the data. So we're using the same data set that we used yesterday. So this comes from the study that I talked about in the first talk. You can look at summary by just running this command, and you should be able to see this data set on your setting. So if you look at the summary, what we have is again similar to what we had yesterday, but today, just as a practice, we are going to use different dependent variable. So yesterday we used binomially coded fixation data. So either we had the values either 1 or 0. 1 means the object was fixated, and 0 means the object was not fixated. Right. Today we're going to do something slightly different. So we have several additional columns loaded here to get that independent variable. So dependent variable. So the data we got, as yesterday's data, we have subject, trial, and the time variable here. We also have the all sample column here that contains some of all samples in the corresponding time bin. And the blink count is the total number of samples that were in the blink event. So that is the just sample that I call it as a blink. And off-screen count is when the participants are not looking at the screen. Right? So that's the count, sample count for that event. Everything is as yesterday, so I'll skip that bit. So we are going to use empirical logic. So empirical logic transforms fixation data as dependent variable today. And the formula to calculate this is this. So we log transform the data, and Y here is the total number of samples that were in the critical interest area, and N is the total number of samples for the current V. Okay. So we can get this N by getting the all sample counts minus blink count and off-screen count. So we are excluding these data that correspond to these events from total sample. So, right, and why we can get the total number of samples that corresponds to count. So we have the count data here. Okay. So we can calculate the empirical logic by taking the log of count plus 0.5 and divide it by this. Okay, so this is the same thing as this. Yeah. Okay. So we calculated that and then put this value into E-log empirical logic fixation. Okay, so this is what we're going to use as a dependent variable for this analysis. Okay, and then we can put plot time course data. It's a good practice to start with visualizing the data. Okay, so I'm going to skip this plot bit, but if we plot this, we get data like this. So this is what I showed you yesterday. We have L1 groups and L2 groups data. showing the fixation proportion on the target, English competitor, Japanese competitor, and unrelated condition. Okay. So I plotted this here so that we can later add the results to this graph. Okay, so I want to start just a kind of practice to see. So the first thing to run cluster-based permutation analysis is to run lots of analysis for each bin, right? And that involves multiple comparisons, and that's not what we should do. But the first step that we take is to do this. So I show you what happens at that stage. Okay, so we can first, example, look at the by subject data to do a by subject analysis. So here, what I'm doing is to get the by subject average. So we're getting the average for fixed. Again, this is our dependent variable, and we are computing means for this per subject, per group, per condition, and time. Okay. And if we compute that, this is what we get. This is just getting the first 6 rows of the data. So we have the subject ID, the language group, condition, time, this is the number of samples, and the our dependent variable, empirical logic, and standard deviation, standard error, and confidence interval. Okay. So we can try and compare the target and unrelated conditions in the A1 group first, and we can use ANOVA by being function from the cluster permutation package to do that. And the usage of this function is you write this function, you put your data, your time bin, and your formula. Okay. And for this case, we run the ANOVA testing the effective condition for each bin. Okay. And we will save the results and do this data set that I just named. Okay. So in this analysis, multiple comparisons are not corrected. So we just run many tests and we're not correcting that for now. Okay. So again, to do that, I'm first taking the data from everyone speakers and only from the target and unrelated conditions. We want to compare these two conditions against each other. And so this summary is now put into this data set. And here is a function that does the ANOVA for every bin. So this is taking the ANOVA by bin from the cluster permutation package. And this is a data set that we just created in this code. So the next one is going to be bin. Right, so the time in this case is a time bin. And the formula be the dependent variable either fixed predicted by condition. And we've included the error by subject. Okay. So if we run this, in this case, I'm saving the results to target unrelated A1 uncorrected. If you look at this, we have the results of the statistics saved for each time bin. Right? So this is, for example, showing the p-value of the of this comparison for this time bin. Right? And we have that for every time bin. Like if you can go to the time bins, we have data from minus 7 milliseconds to 950 milliseconds. Okay, so we have 2 seconds time window here. And we can try and subset the data and get the time bins in which the effective condition is significant. Okay, so if you look at the first bin, the effect is not significant, so there is no significant difference between the target and unrelated condition. From around 600 minus 600 milliseconds, there is a significant difference between the target and unrelated. Okay, so we just take the data where the p-value is more than 0.5. This is what we get. Okay, so if we run lots of ANOVA, what we can get is significant effects from minus 600 milliseconds, and that will continue until the end. Okay. Okay, we can do the same for L2 speakers. So this time we are just taking the data from L2 speakers, the same set of conditions. And again, the function we use is ANOVA by bin, and we are putting in the data set, time, and the formula for ANOVA here. Right. And again, we can take the time windows where the p-value was smaller than 0.5. And for reduced speakers data, we get the first spin that corresponds to minus 350 milliseconds. Okay. And that will go until the end as well. Okay, so if we run this ANOVA many times, what we get is for A1 speakers data, we have a significant difference between the target and unrated conditions starting from around 600 milliseconds before the target was onset. And for A2 speakers data, we get also a significant difference between the target and unrated, which started from minus 350 milliseconds before the target was onset. Right. So, but as I said, this involves multiple comparisons, right? So the p-values are not corrected, right? So because I ran the same test, in this case, 40 times, right, the chance of getting false positive is very high, right? But we can compare what we get later with what we get here. Okay, so this is what we get if we run multiple comparisons without correcting the p-values at all. Okay. So, at the next step, we can try and adjust p-values for multiple comparisons. And what we get if we apply the standard non-periodic correction, right? So this is not a part of the analysis involved in cluster-based permutation analysis. Okay, I just want you to have a look at what we get when we don't apply the non-periodic correction and when we apply the non-periodic correction and what we get if we run the cluster-based permutation analysis. Okay, so this is just for you to compare the results to. Okay, we can simply apply the non-periodic correction by using this p-adjust function. That was a function. So this is just what I named. Okay. And then by specifying the methods to non-periodic. Right. So if we run this to the result that we got, we have the original p-value here and the non-periodic corrected p-values here. So in this case, because we had 40 ANOVAs, we're dividing the, or in this case, we're multiplying the p-values by 40. Right, so that's what we have in the p-value here. And if we do the same and only take the time windows where the p-value was smaller than 0.5, 0.05, and what we get is a significant effect starting from now minus 500 milliseconds. Right? So in the previous data set where the multiple comparisons were not corrected, this started from minus 600 milliseconds. Right. So this makes the effect to be conservative compared to the non-corrected results. Okay, so if you look at the two groups data and do the same, you also get slightly different data. In this case, we have one significant time being at minus 250 milliseconds, and then the next time is actually minus 100. So in between, there was time beings where the effect is not significant. Okay, so that is what we get if we do many ANOVAs and apply non-periodic correction. Now, next, we want to look at cluster-based permutation analysis. But I noticed before this workshop that this script that I published together with the paper no longer works. And that is because one of the functions used in the cluster perm package no longer works. So unfortunately, the data, the script presented here now don't work. So I will present an alternative here, but I try to fix this when the function works again. So I skipped this part, but again, as I said, I'll try and fix this bit once the issue for the package has been fixed. Okay, so I skip this bit and go to the alternative way to run the cluster-based permutation analysis. So the previous one was the cluster-based permutation analysis based on ANOVA, but here I'm running a cluster-based permutation analysis based on linear mixed effects modules. Okay, so as I said, the first step for the cluster-based permutation analysis is to run either t-test or ANOVA or linear mixed effects module, kind of as a base test, right? And then you run that many times for every bin. And that test can be a t-test or a linear mixed effects module or G-linear, whichever is fine. Right. So in this case, I'm using LME as the base model. Okay. The first thing we can do is to prepare our data. Right? Because we are running LME, we don't have to summarize the data by subject or by item at the beginning. Right. So I'm just taking from the original data set, just select the subject and item and condition, time, language group, and independent variables, just selecting what we need for the analysis and filtering the data so that we only have everyone speakers data and the two conditions we want to compare. Okay. And this is doing the same thing for two speakers. Okay, so the code is identical except for I changed this language to L2. Okay. So now we have the data we can use for the analysis for L1 speakers here and for L2 speakers here. Okay. Okay. In this case, in this tutorial, I'm comparing the target and unrelated condition against each other. So I'm just going to post this categorical variable using some coding. Okay, so that's what I'm doing in these codes. Okay. Okay, so for this tutorial, we can use a package called Permute and run the analysis based on linear XFX model. Okay. And if you want to run the generalized XFX model, that's also possible. You just need to change cluster from LNER to cluster from GLNER. Okay, so this is the formula to run the model. So again, we are taking the cluster from LNER function from the Permute package, and we want to test the empirical logic dependent variable predicted by condition. Right. Here I'm running a very simple model, just random intersets by subject and item, but you can decide that based on your design or data. And this is just the data that we created at this stage. Okay. And the data in this code, I just specify which column contains the time variable. So in my case, it's called time. Right, so I just specify the column name that contains time variable. And the number of permutation here is now set to 1, but ideally you should set a larger value because it requires a larger number of permutation to get reliable data. Basically, the larger the better, but the larger, the longer time you need to run the analysis. So somewhere around 1,000 to 2,000 would be a good number. But in this tutorial, I am setting it to 100 to save time for you to open the tutorial. So ideally, please increase this number to at least 1,000 when you want to apply this course to your own data. Okay. Okay, so if we run these codes, we can get the results, and that is stored in whatever you call this. Right? So if you run this and then you save the results here, you can call the results. And I'm just adding the new column for the language group because this one didn't contain that. Okay. So I did that using these codes, and in the code here, I'm just merging the two files. So we have the A1 speakers results here, and there's the speakers results here. And here I'm just binding the two data sets. So A1 data here and A2 data here. So if we look at this results that contains both A1 and A2 speakers data or results, or we get something like this. Okay. So we have the time being ID, and measure is a dependent variable. The factor, so this is just testing the intercept and testing the effective condition. Right. This one, I forgot what that was, but I was using that for here, beta. And then this is the t value here. And then cluster is showing the sign. So if it's 1, I forgot what that was. Let me double check what this was. Right, cluster should correspond to the first or second. So now the idea of the cluster. So if it's the first cluster, it's given 1. If the cluster is not significant, then it's called 0. If the second cluster, it's given 2. Okay, the cluster mass is a cluster mass statistic. So it's in this case, sum of all t values for that cluster. Okay, so if it's in the same cluster, for example, this one is in cluster 1, right? So these all have the same cluster mass values. And p-value is the p-value for the t-test for this specific time being. Right. And then here we have the p-value for that cluster. It's not the independent test, but for the cluster. And we have the language value that we add at this stage.
Aine?
Yeah.
Janina has a
Yeah,
question.
just like what are the units and like the numbers and the cluster mass? Like what is it? Is it just an ID or?
Sorry, which one?
What's the unit of the cluster mass? It's the
Oh,
sum of the t value, right?
Yeah, is it?
Yeah.
exactly. Yeah. So if we add all the t values in that cluster, that's what you get.
Thank you.
Yeah. Okay, so that was the results. So we can just take the significant cluster from this data. So because this contains the data and also non-significant clusters. So we can extract the time bins where the effect was significant or the cluster was significant. So we are taking the same data set here and filtering the data based on the factor condition, because we're not really interested in the significant intercept, but the significant affected condition. So we're just taking the data where the factor is condition. And here we are taking if the cluster mass, so in this case, if cluster mass is not NA, and when the p-value for the cluster is smaller than 0.5. Okay, so we filter the data based on these and treating the time as a numeric variable and grouping the data by the cluster and the language group. And here we are adding some variables. So the here we have the cluster mass. Right, so cluster mass, we are taking the minimum of the cluster mass, and then p cluster mass is the minimum of the p-value for the cluster mass, and then bin start is the start of the time bin, and bin end is the end of the time bin, and t-value here, I'm computing a mean t-value here. And then, because we have a positive and negative cluster, so if the target was exceeded more than the unrelated condition, we get a positive cluster. If the unrelated condition was exceeded more, then we get a negative cluster. Right? In this case, we only have a positive cluster because the target was always fixated more than the unrelated condition. But we can include the sign here as well. So if the t-value is smaller than 0, then we call it as -1, so it's a negative cluster. And if it's a positive cluster, we call it as 1. Right. This is useful if you have both a positive and negative cluster because we want to distinguish when plotting the results. Right. And then I'm just converting the time again to millisecond. So the time we had here was the ID of the bin. So this is the first bin, second bin, and third bin, but they don't correspond to milliseconds. Right? Each bin contained 50 milliseconds data. So I'm multiplying it by 50 and doing -1,000 because my first bin corresponded to -1,000 relative to the target word onset. Okay. And the same thing here. Then I'm treating Sine as a factor. So this is not a number but a factor. Okay, so if I run this, I just get the significant cluster data here. So we have 2 clusters, 1 for each language group. And here is the cluster mass that you'd be reporting when you report the results. And here are the p-values. And these are the starting and ending bins. So the final bin was 40, the last bin was 40 for data. And this is the bin ID that corresponded to the first starting time bin for the cluster. And here's t-value sign. Again, these are both positive signs. And then this is how we calculated time, right? So based on these bins. So bin 8 corresponded to -650 and bin 14 corresponded to 350, right? So now we have this result, so we can use this to add these results to our plot. And this is what I'm doing at the code here. Okay, so when I created the plot, maybe let me quickly go back. So I saved this ggplot to fix.plot. Okay, so I can now call this when I want to add the results. So that is what I'm doing here. So I'm calling the fixed plot that I created when I plotted the data. And now we are adding a new color at the bottom. So that's what you get at the bottom of these plots. Okay, so I'm taking a data that we just created. Yeah, so that's this data set or this result. And we are now plotting the on here the line from the time starts. So we're taking the value here and then the time ends. So to here, I'm putting the y-axis to 0 because I wanted to put this thing at the time 0. If you wanted to put it at the top, you can change this to 1 or wherever you want to put, right? And then I'm changing color depending on the sign. In this case, I only have a positive cluster, so I don't really need to do this. But if you want to change this to your own data, it's probably nice to change the color depending on whether the cluster was positive or negative. So this is how you can do it. Right. And height is the height of this. So this is actually plotting an error bar. So if I'm putting the height 0, because otherwise it will be plotted like an error bar. I don't want to put that the error bar thing there. So that's why I put the height 0. This is just a line width, and alpha is the transparency. And so this is like a half transparent color. Right. And then I'm not showing that to the legend. Right. And in this case, I'm
Aine, sorry.
Yeah.
Oh, one question.
Yeah.
Okay, go ahead and then.
Okay. Right. And then you can change the color. So if you wanted to, for example, use blue for a negative cluster, this is how you can do it. Again, in this case, I'm not really using it, but in case you also have a negative cluster. Okay. So if you run this, what you get is this added line. You can compare this graph to what you had when you plotted the data, right? So this is the original plot that I called when I run this thing here. So it's just this line added at the bottom, right? So you can see that, okay, we have two clusters. One is here, and then you can see the corresponding time being here, and then the other is here for the two speakers, right? So this is one way to visualize the result of the cluster-based permutation analysis.
Yeah.
Yeah, the questions now, because you have 4 conditions, like what are the cluster stuff comparing?
Yeah, you can, when you want to, for example, compare, let's say English compressor condition, but the unrelated condition, you can just change the condition here to English compressor condition and run the same thing.
This is target versus unrelated.
So you removed, it's just 2 conditions, it's just 2 levels.
Yeah.
Yeah.
2, right?
Anna's asking Aine if you can only compare 2.
Yes, cluster permutation analysis is for comparing 2 conditions.
Yeah, it's just then misleading a bit to plot 4, and to plot the cluster. Right?
May I ask
Yeah.
a question about the binning? So, because the binning seems to be crucial when the effect happens, because it is showing you the first time bin where the first cluster. I know, do you have a guideline what to choose for time bins depending on your sampling rate?
Yeah.
Right.
yeah.
Yeah.
Did
So
you
here
hear
have
that,
a,
Aine?
yeah, I
Okay.
got that. Yeah, so here you have a smaller bin, then you are essentially running more models, but the number of models you run is actually not affecting this data set, because at the end you are comparing the cluster against null distribution. So you're not really comparing the results for each time bin against null distribution. So how many, like, what t-test you run or LME you run at the beginning, it doesn't really matter. So the binning really only matters when it comes to, so when you have a cluster size, if you only have a 50 millisecond bin, of course the cluster starts only every 50 milliseconds. And if you have a 20 millisecond beam, for example, then each cluster can be a bit more, how do I say, specific, or so it can start at each 20 millisecond interval, right? But the cluster-based permutation analysis can't really be used to say when the effect started or when the effect ended. So also in that sense, beam size doesn't really matter that much. So you can go for standard something around 20 to 50 or something like that.
Okay, but okay, yeah, that makes sense. But in general, do you have some kind of guideline what time bin I should use? Because I guess it depends on the sampling size I have. You showed in the beginning that if you have a 50 millisecond time bin, in your case, then you have 4 observations in a time bin. And that depends on the sampling rate I use during recording.
Right. Yeah. So sampling rate is something important to check. I think like recent eye trackers can measure 1 sample per millisecond or something. So I mean, if you wanted, you can even go for running the thing for each sample. That's probably not realistic. But I think one thing to consider is the effect that you're looking at. So if you think your effect lasts relatively long, I think it's relatively not problematic to take a relatively large beam, right? But if you think your effect might not last for a long time, like say only 100 milliseconds or something, then it may make sense to go for a smaller time beam.
And Aine, you can't compare so you have in the end L1 clusters and L2 clusters, but you can't compare those two, right?
Right.
Yeah. So you can just say that L1 has this much time window, L2 has this, but you can't say that, these are different or whatever, statistically different from each other.
In terms of like onset of the cluster.
Yeah.
Yeah.
Right, exactly.
Yeah.
Yeah, that's great.
Yeah.
Can I ask something related? Could you, like, instead of doing the mixed models with just condition, could you like add the interaction with group there and then like check for which cluster the interaction is significant, if you are interested in the difference between groups as well?
Right. No, in this case, no, because cluster-based permutation is really about comparing 2 conditions. So it's not really suited to look at interactions. But if you want, that's one kind of workaround to that. That is, if you wanted to say test 2 by 2 interactions, like one way is to compute the difference between the 2 conditions for like one effect, and then test whether that difference is different for the other 3 conditions. So do you know what? Let's say you have.
So you
let's say
mean
you have condition A. Sorry, go ahead.
no, go ahead, Aine.
Okay, so let's say you have a condition A and B and group A and B, right? And then let's say you want to test an interaction of condition by group. Okay. One way is to compute the difference between condition A and B within each group, and then you have the difference score for each group, right? And then you can test whether the difference score is different in the groups.
Yeah.
So the comparison is always one condition or group versus another.
Okay.
Yeah.
Thanks.
Any other questions from the Zoom room so far? Okay. All right. I think we can go.
Okay. So we got the results, and we are going to the section on how to report the results. So when you report the results, we report the cluster sum statistics and the p-value. So that's pretty straightforward. If you go back, that's what you have here. So the cluster mass statistics here, and you have the p-value here, right? That's what you report. And as I also said in the talk, when reporting the results, you would want to be careful about how to interpret the results. So not to say like this effect started at this time being or ended at this time being, right? So I want to do a quick quiz about how to report and how not to report the findings. So considering this point, which of the following statements are inappropriate when reporting the results from the cluster-based permutation analysis? Okay, so you can do this more quiz and then select all that apply. I maybe give you a few minutes to go through that.
Okay, I think at least the room reached a decision. So I
Shall
know,
we call it,
check.
or
Yeah.
anyone from Zoom?
Yeah,
Goodness
so
me.
we said that, what was it, guys? Two, the second,
Yeah.
two,
5 and 6.
2, 5, and 6 are not good.
2, 5, 6.
Yeah,
Right.
I don't know.
Okay. Hey, it's look at it one by one. So the first one, we found two significant clusters, one ranged from this time to this time, the other ranged from this time to this time. And this is fine because we are talking about the clusters, right? It's based on the result that you found. So this is fine, not inappropriate. So this is okay to say. The second one that you found a significant cluster which suggests that the effect started from 300 milliseconds, and this is inappropriate because we can't, based on the significant cluster, conclude that the effect started from the beginning of the time being. Okay, the third one, we found a significant effective condition. This corresponded to a cluster beginning around 200 milliseconds. That's also fine because again, we are talking about the cluster and not the effect. The fourth one is also fine because the cluster, again, we're still talking about the cluster and the cluster in the data extended from this pin to this pin, or this time to this time. Okay, the fifth one, the significant cluster in group 1 range from this time to this time, and the group 2 range from this time to this time. This suggests that the effect occurred earlier in group 1, in group 2. Yeah, this is not correct. This is not correct. I mean, this is not appropriate because we can't really conclude that the effect occurred earlier in A1 and A2 group. Because although the cluster beginning time 200 versus 350 was earlier in A1 group, so in group 1, but this doesn't suggest that this effect started at 200 or started at 350. Right, so we can't, based on this, conclude that the effect started earlier in group 1. The final one, the significant cluster in group 1 ranged from, again, this time, and in group 2 ranges from this to this, and suggests that the effect is more longer lasting in group 2. It's very tempting to conclude this, but this is also wrong. We can't conclude that because the cluster-based permutation analysis doesn't also tell us how long the effect is. So I hope this should make it correct. Yeah, right, that was correct. So, yeah, everyone who was there got it correct. So congrats. Yeah, so the important distinction is whether we are talking about the effect or the cluster. It's the cluster is what results show. So we can talk how the time range of the cluster, but we can't, based on the size of the cluster, conclude that when the effect started or how long it lasted. Okay, so that was the how to report the results. So let's go to the next section. So that is it's end with exercise. We've got two exercises, but so this exercise is what I originally prepared for the ANOVA-based cluster-based permutation analysis, but we didn't do this. So let's go to exercise 2, which is using the cluster-based permutation analysis based on LME. So this is the original model that we used for the tutorial. And so based on this code, please write a code for the same analysis based on a generalized linear mixed effects model to test the same question, but including a bisubstrate and bi-item random slopes for condition and bisubstrate and bi-item random intercepts. And assume that we have a column with a dependent variable binomial fix. That is how it is called. Again, we don't have this data in here, so we don't run the code, but that just write the code to run this analysis. Okay. And you can check the solution by clicking here, but don't click run code. Okay.
And then maybe we can take a quick one because it's 10 now, 11
Yes.
now. So yeah.
Right.
Or
Yes,
10
boy.
now,
Yeah.
and we have 2 more hours and we have to go through 3 more things. So yeah.
Yeah. Okay, yeah, for those who haven't finished, you can take the solution here, but let's move on and see what you should have changed to. So this is for solution 2, for exercise 2. Okay, so for this exercise, you have to change a few things. So you need to change the cluster from LMER to GLMER to use the generalized linear mixed effects model as a base model and change the dependent variable to the binary fix. That's what you want to use as a dependent variable. And change the random effect structure from this simple random effect structure to this to include both by subset and by item, random intercept and random selves. Okay. Okay, that's all for cluster-based permutation analysis. Any questions?
Any questions from the Zoom room? No, I don't see any hands. Okay, I think we're good.
Okay. Okay, if not, then please close this tutorial. I will stop sharing and close this, and then open the next one. Let's go to B dot. So I type the command in Zoom. So you can run this to launch this tutorial. You need to close the previous tutorial and then stop running the tutorial to launch the next one because we can't open multiple tutorials at the same time. So you should see a stop button in your R Studio. So please click that to stop running the CPA tutorial first. Okay. Okay, are people opening? So the B dot again is used to test differences in the time series. And as I said during the talk, I couldn't apply B dots to my own data. So this is showing not successful application of B dots, but the same code should work if you wanted to apply to your own data. But again, as I said during the talk, you'd probably need a smooth curve in your data. And to do that, you probably need to have lots of items in your experiment. So mine is still actually opening and haven't opened it.
Okay. I think most of us opened it. I knew.
Okay, good. Actually, I'm still trying to open my own, sorry. Managed to open this in the browser, so let me share that version. Okay, hope you can see. Okay. Okay, so as I said, this is not a successful application of the VDOT analysis. So if you wanted to see the successful application, you can check the VDOT vignettes here. Okay. But the code I present here should work for other sets of data as well. So that's the notes. Okay, the setup is identical to what you did for the other tutorials. It's just that you need slightly different sets of packages. So these are the packages that you need for VDOT analysis. Okay, looking at the data, again, this is the same set of data we're using. So we go through it quickly. Okay, so it contains the same set of columns that as in the data set that we used for the cluster-based permutation analysis. Okay, and here we are also using the same dependent variable as in the cluster-based permutation analysis. So we've already looked at how to compute the empirical logic as the dependent variable. Okay, so I'm going to also skip these parts. So here, I'm doing a slightly different comparison to what we had previously. So we are now plotting the fixation proportion to the target only and comparing the looks to the target between L1 and L2 speakers. Okay, so that's why this graph looks very different. So this is only plotting the fixation proportion to the target for L1 speakers and L2 speakers in blue and pink. Okay. Okay, and we can compare the difference between L1 and L2 speakers. Okay, and this is how the data look like. Okay, so running the B dots, we can first create a bi-subject summary of the data. So we're taking the dependent variable here and then creating or grouping the data by subject and language group and time, right? And then we get the by subject and by time averages here. And then we can fit the curves. Right? So because now we have the looks to the target, we can use the for parameterogistic fitting function. So to do that, we are calling the function called v.fit, and this is a function to fit the curves. Okay, and this is from v.package. package. So we are calling v.package package and v.fit function. We are using a data subject that we created in the previous step. Just to show you, this was called subject that. Okay. Right, so that's the, sorry, next one, data. So this is just telling the function that this is the column that contains the subject ID, right? And so you put that, and the same for the time. So this is the column that contains time information. And Y here is your dependent variable. So in this case, E-log fixed. And then this is subject group, and then the curve function you want to use. So in this case, we want to use a full parameter logistic because we are modeling the target. So that's how we put logistic here. Okay. Okay, so this, if we run this will fit the curves to each subject. And we can check or visualize the fit using this plot function. So we just plot what we got in the previous code. Okay, so if you plot this, we can see the model fit or curve fit or fitted curve and the observed data, right? So the observed data sometimes don't look very smooth. And of course, this one is very shaky. This one is also not so smooth, right? So model fit is always a smooth line, but the observed data is not necessarily always smooth, right? So we can actually see that lots of the curves are not well fitted. That is, the fitted curve is often away from the observed data, right? And we can just check through the data for each subject, but for most of the subjects, the data are not looking great, right? And this one looks relatively fine, but most of the time the data are not looking so great, right? So we can look through until the end, but the overall pattern looks the same. Right. And so this is how we can visually check the data, and you always should visually check the model fit. Right. And then we can also check it using the numbers that we can see here. Right. And so Zedov proposed that if we get this R2 number larger than 0.95, it's seen as a good fit. Okay, so we can also check it by looking at these numbers, and our numbers are nowhere near that range. In fact, I think none of the numbers are above 0.95. And we can also check that just running this this code. So this is taking subject fit, and we are taking what is called a fit code. Okay, and here, right, I don't remember what. Oh, yeah, so one fit code 1 indicates a reasonably good fit, when the RT value is larger than or equal to 0.8. And fit code 2 indicates it's a poor fit. The R2 value is smaller than 0.8. Right? Fit code 0 also indicates a poor fit. So we can check for, this is showing the code. So if it's 1, it's reasonably good. If it's 2 or 5, it's poor fit. So most of the data in this experiment were either, they were mostly poor fit. Only 10 subjects had a reasonably good fit. And none of the subjects had considerably good fit or good enough fit. So as I said, we should proceed with this, but this is how you can check the curve fit, how you can fit the curves, and how you can check the curve fitting. Right. For other course, you can check this vignette to check what, for example, 3 means or 4 means or 5 means. Okay. Okay, so we've seen that alpha curve fitting didn't go well. We can try and refitting the curves using the refit function, so b.refit function. So we can just take the same data set and then here decide which one we will refit. And so here, if we say 1, we basically fit the data to everything that's after 1. So if the code is not 0, then we refit. So that means if fit code is 1, 2, 3, 4, 5, or 6, that is basically everything. So we are refitting data to everything in this case. If you want to refit the data to, for example, if the code is 2 or 3, then you can put 2 here. So in 2 or 3, 4, 5, or 6, okay, you can put 2 here. Okay. And I just by default set the quick refit to true. Okay, if you refit the data, we can try plotting the refit data. So we can, again, visually check the refitted data, but it doesn't seem to be making a much difference. We still see that the observed data are not so close to the fitted curve, and the R2 values are still not so close to the 0.95, right? And overall, it seems like the case, right? So refitting really didn't improve our curve fitting. So again, we shouldn't really go ahead with this data. Still, the subject who had reasonably good fit still remained, and all of the subjects had a poor fit.
Oh, sorry, can break it off.
Yeah, no.
Yeah, just a quick question. So what are you doing exactly with this refitting? I mean, they still all get the same type of curve, right? So what's happening?
Yeah. No, it tries to with a slightly different function. So it is slightly different, but in this case, because the observed data is still not a smooth curve, right? So it's not really possible to fit a good curve to these observed data sets anyway.
Okay. Okay.
Yeah, sometimes refitting works if there's another function that fits well to your data, right? But in this case, it doesn't seem to be the problem of the fitting function.
Okay, but you can't like give different curves to different participants or something. It should all be.
You can.
Okay.
Yeah, you can do that too. Yeah, but so for example, if you wanted to give a double Gaussian curve for this participant instead, for example, you can do that too. But the problem in this case seems to be that the curves for the observed data are not so smooth, and then the fitted curves are always smooth, so they don't prove very much anyways.
Okay.
Right.
Okay, thanks.
Yeah. Okay, so that's the refitting that didn't work. So if you get reasonably fitted curves, you can go ahead and run the model. I will run the model here anyways, but what you will see is the result of a poorly fit curve. So you shouldn't really trust the result of this model. Okay. But I will show you what will happen if you try to go ahead and run the model, ignoring the poorly fit curves. Okay. So to run B dots, you will need this b.root function. And formula is just the dependent variable and independent variable here. So e log fix predicted by the language group. And this is the data that we had. So this is putting the data set here and the number of iteration. For this, ideally, also you should have at least 1,000. And this is the alpha value we're using. So if we that's just a p-value threshold, right? And but when we run this, we get the summary of this result. So this, I put the result into boot one, so you can get summary to boot one, right? And here, if we try and plot the results of this model, what we get is like this. So this is trying to plot the data together with the standard deviation, right? What we can see is that the standard deviation is very, very large. That basically the standard deviation for the L1 data and the L2 data mostly overlap with each other, right? And for the difference curve as well, it's huge. The standard deviation is huge, and it basically covers a huge area here. Right? And this is the result of the poorly fit curve. So if the curves are reasonably fit, you should get much smaller standard deviation here, right? So that you should be able to reliably estimate when the difference was significant. But when the standard deviation is this large, basically there's no difference at any time points. But that doesn't seem to be what's happening with the data.
Aine, quick question again.
So how many, is there sort of a rule of thumb for how bad the curves can be fitted to still proceed? So how many bad predictions you have?
Yeah, you should, you can check that using the fit code here. So if your fit is at least 1, then you can proceed. For what these codes mean, you can check this here. But if it's reasonably good fit, that's if the R2 value is larger than 0.8, and if most of the subjects fit in that range, then you can proceed. Right? If your if the R2 values for most of the subjects are below 0.08, then you shouldn't proceed. That's one of the the threshold you can rely on.
But like, what do you consider most of the subjects? How many?
You can actually exclude the subject you should exclude the subject that resulted in a poor fit. So that's like, okay, how many subjects are you okay to exclude, right? So that's also similar to that kind of question, right? So obviously you probably don't want to exclude half the participants from the experiment, right? But say like 20%, and that's some people might be okay, some people might not be okay. So that depends. Also depends on how many subjects in total you have, right?
Okay,
so
you
that
have
can't be an exact number, but yeah.
But you have to exclude them. All
Yes, yes.
Okay. Okay, thanks.
Okay. Any other question?
Yes, can I ask a question? I was just wondering, so what we're looking at, what we were looking at run the model before, so the bootstrapped fits, that's already based on the model structure that we have, or not? Or is that, no, sorry. Is
this
yeah. Is this is this just the actual data as it is, and then
this is just
case,
putting
grouped by first language, or?
Yes, this is just putting the dependent variable here. So this value predicted by the language group. So we want to test the effect of group. So if you wanted to compare L1 group versus L2 group, that's what we put here. So independent variable goes here and dependent variable goes here.
And say, for instance, that there is like an additional factor that might explain the different curves for each subject. Is that something that you could already include here, and that might improve the fits, or is that not?
No,
do you
that's
understand
before.
what I mean?
Yeah, that should be done before running the model. So you first fit the curves.
Okay.
Yeah.
So sorry, I just didn't get the curve fitting that we did. That was already based on the the eventual model structure that you're going to use in the with your variables of interest.
No, this
in
is
this
just
case-
using, okay, so we want to fit the curve for each subject and we just
Mhm.
putting the time and then the dependent variable here. So it's not based on the model we're using.
Okay. Yeah. Okay, yes, then that's clear to me. Thank you.
Okay.
Oh,
good.
sorry, adding to that, I guess, Tim, your question was whether you can, for the group, we have language, but can we put in more, right? Like subset by.
Yeah, I just I didn't understand whether the curve fitting that we had done at like the screen that Aine is sharing right now, whether that was already based on some sort of fixed effect, or sorry, just any kind of effect that we are interested in, or whether it's just literally
no.
plotting for each subject like the best fits for like the observed data.
Right. So this is based on the observed data and not based on what we want to test.
On any kind of predictors. Okay, yeah.
Right.
But
Got it,
Aine,
thank
you
you.
can, for a group, if, you know, right now you're not looking at condition, obviously, but if there was condition, can you do like group equals C language and
Yeah.
condition? Yeah,
Yeah.
okay.
That's because we want to fit the curve differently for different conditions.
Yeah, okay.
Right. Yeah. So that was the curve fitting where were we at. So we run this model that we shouldn't really run based on the model, but we run it anyway. But if you do that, what you get looks like this. And then we will actually see later that actually based on the data, it does seem the difference between A1 and A2 group. So this difference that sometimes goes to like 20% fixation proportion difference was not detected at the P dot, but that's probably not because this effect is not significant, but rather the curve fit was very poor and we just ignore it and run the movie, right? So that will result in a huge standard deviation and won't produce a reliable or accurate result. So if the curve fitting is poor, you shouldn't proceed. Okay. So as I said, I don't have a successful example, but you can look at the B-dot mechanics for the successful application. Okay, so we can now proceed to the exercise. So in this tutorial, we wanted to compare the target fixation proportion between the A1 and the groups using the same data set. Right, so this is a data set that we'll be using, and the dependent variable was empirical logit. Right. So the exercise is to write a code to fit the curves to the English competitor fixation proportion and plot the fitted curves to and observe the data. But again, don't run the code. We produce an error. Okay. Just like you to write the code and then you can check the solution by clicking the solution.
Aine, I have a quick question.
Yeah.
Can you run the model? Can you go back to the run the model one? Yeah, and then where do you look at this, whether this was significant or in the summary?
Oh, in the summary, you can't actually really showing anything here.
Okay.
Yeah, because it's now just false. So it didn't detect any difference. So there's nothing to record in this summary. But if you found some effect, it should show up in the graph, like the states shouldn't overlap. And in a different curves, you should be able to see which time windows show a significant effect.
Okay, but even if the data was well, like you can't see it in the summary, like or is this just because this data wasn't good that it's just giving you? Or
Right.
where do you see?
Right, you should be able to see it here.
Right, okay.
Yeah. Yeah, in this case, it doesn't have anything, so it's not.
Right.
But if you have something, you should be able to see it here.
I see. Okay. And what's that formula there? It's different from the formula that you actually ran. This E-log fix mini.
Right.
That's just
I
what they're
actually don't
computing,
know.
right?
Yes.
Okay, so it doesn't matter. That's just gonna come out from the summary.
Right. So I'm afraid I don't know what, yeah, this
Yeah.
one.
I was like,
Sorry.
what? That's very different from the. Yeah. Okay. All right. Thanks. Aine, there was a quick question in the room. How does this one, because before you said that it could give us the timing of when the effect occurred, how do you How do
Yeah.
you extract that from the
Yeah.
model? Yeah.
Right. We probably, so I was actually opening Microsoft once and then share the other screen. That is maybe this one. So this is, can you see?
Yeah.
Yeah. Okay. So this one is showing a successful application period through the BigNet. Okay. So if we have a good curve, the SD should look something like this. And if you have a significant time window, that's highlighted in yellow in the results. Okay, and you can also see it in here. So this is a starting time point. So when the effect started, and then this is the ending time point. So when the effect ended. So if we do a model fitting is successful, you should be able to get the numbers here. And then that's again highlighted in these graphs.
Okay, cool. Thank you.
Yeah, and also figure out what this was. So this is, if you remember, this model is the four-parameterogistic and double Gaussian curves, right? And they have different functions. So four-parameterogistic has the smallest point and the highest point and slope, right? And then double Gaussian has the peak and then the how it's distributed. And these values are for these curves. Like, okay, what's the highest point or how the distribution is? Very much detail, but this is about the curve. So that's different depending on which function you use to fit. So this is for double Gaussian, the one we had in the tutorial is for four parameters.
Okay, cool. Thank you.
Yeah. Is it?
How is it looking? Look good? Or yeah? I think most people are finished.
Okay. Yes, I have published it and you can check the solution here. It's check for you should have changed. And so because this time you want to test or you want to take the English contextual condition, so you should have filtered the data, taking in the English contextual condition. And because this is a competitor, right, you expect the fixation proportions to go up and down. Right? So ideally, you want to use double Gaussian for it instead of the four parameter heuristic. So change that to double Gauss instead of heuristic. And we also had to add the concave one, so I actually didn't explain that during the tutorial. But if you, let me actually go back to the model fit. Right, and so if you want to fit a double Gaussian, you need to add either concave true or false. If it's concave true, the fixation goes up and down. If it's concave false, it goes down and up again. So you want to specify which direction you want to fit that. Usually, I think it's true, unless you expect a pattern where the fixation proportion drops and then goes up again. Right, so that should be added if you fit the double Gaussian curve. Any question about the exercise?
Sorry, Aine, did you say something?
Yeah. Oh, yeah. Any questions? Sorry.
Oh, oh yeah, should we take a break now then? Okay, so we'll take, what time is it? 10:30. Aine, how many, the other two, can we go through it in, if we take 15-minute break, an hour and 15 minutes?
That's good. Yeah.
Okay, so let's
Right.
take a
Yeah.
15-minute break. So we'll come back at 10:45 Norwegian time. Okay, sounds good. All right, see you guys back soon. OK、アイネさん。じゃあ15分休憩取ってください。はい。
はい。
All right. Okay, Aine, the floor is yours.
Okay, I will share the screen. And please don't see tutorial for GAM now. So I again post the command you should done in the chat. Right, if you open that, you should get this. So as a reminder, GAM is also used for testing whether two conditions are different, and GAM can test when the effect started and when the effect ended or how long it lasted. So that's what we will get after running this module. The setup, you already know this page. We additionally have two packages that we're using for GAM, which I marked here. So we are still in the same set of data. If you read the summary, you will get the same summary. Let's skip this bit. You already know the data. Okay. So for this analysis, we use the target and unrelated conditions, and so we will drop the rest of the conditions. It's just filter data, just take the target and unrelated conditions, and drop all the labels we don't need. Okay. Here we are also using the empirical logic, so that's the same computation that we did before. We're taking the log of the samples that landed on either the target or unrelated condition and taking all the samples in that bin. And here, one thing I'm doing in addition is this thing. So I'm adding a column called age start and time. This is putting true if the time is a minimal time. So what this is doing is to set true if this is the first bin in the data, right? And we need to know that when we calculate the autocorrelation. So that's why I'm putting that here. Okay, so every other bin, so all other bins have false. So if our bin starts with 0, then only the bin 0 has the true in this column. Okay. Okay, so that's what I added. If we plot the data, we already know how the data looks like. So again, we only have the target and unrelated conditions here because we can only compare two conditions. Okay, so that's what we are using as data. Okay, so to run GAM, we first take the data for L1 speakers and L2 speakers. So this is just filtering the data, just taking the L1 speakers data or L2 speakers data and put that into L1 dot and L2 dot respectively. And we are coding the conditions using the sum coding. So that's what we are doing here. Okay, so that's the preparation. We can already then fit the model. Okay, so GAM has a bit complicated way to specify random effects. So that's what we mainly look at when we fit the model. So if you are familiar with LME, I think this bit you already know. You put the dependent variable first, and then you predict the right? So this is testing the empirical logic predicted by condition. And the rest of it, this is probably a bit new because this is specifying random effects, but not in the same way as LME or other other models, you know, right? So what we have here, first we have this smooth, S is smooth, and time by condition, right? So this is telling the model that you want to model time differently, separately for condition. So you want to model time differently for target and unrelated conditions because you expect different patterns for different conditions. And the rest, these two are the random intercept and random slope. Okay, so this is fitting smooth, and I'm including this BS equal FS, and FS meaning faster smooth. And if we put this, we are modeling both the random intercept and random slope for subject and item. So this one time subject and then by condition. This is modeling the by subject random intercept and random slope for condition. And this is doing the same for item. So we just changed this from subject to item. Again, we are modeling random slope and random intercept for condition by item. And finally, we are specifying data we use for this. And the function we are using to fit this is called BAM. And this is from the MGCD package. Okay, so BAM is the function we use to fit the model. And if you want to fit separate random effects, for example, if we just want to set the by subject random intercept, you can add this. So smooth subject, and then we can put VS equal RE. Okay. And then if we want to put random slope, we can specify that using this. Okay. Right, so this is again slightly different from how you specify random effects and slopes for AME. So this is how we do it. And of course, if you want to change this to item, just change the subject to item. Okay. But if you put random smooth, factor smooth, you have both random effect, I mean random slope and intercepts covered. So you don't need to additionally put these in the model. Okay. So using we are doing the same thing for two speakers data here. So again, we are fitting the model using the function BAM and testing the empirical fixation predicted by condition. And we're using the same random effect structure for the two data too. You get a warning if you run this, but it's okay because this is just saying that we have smooth over time, both in random effects and fixed effects. So we know that, so we can ignore this warning. So if you get the model, the summary of this model for A1 speakers, we get something like this. So these are the significant effect of smooth terms, like looking at the interaction of time by condition. But as I briefly mentioned during the talk, these are really hard to interpret and don't really know what the, for example, interaction of time by condition tag really means. We look at how we should interpret the data, or rather than looking at the model output itself, we can plot the difference curve, and that's what we do later. But we're fitting the base model now to get the autocorrelation parameter. I guess we don't really have to look into these. But yeah, this is just what we get when we get a summary of the data. So as I said, what we want from this base model is the autocorrelation parameter. And you can get that by running this from HStack package and start value RHO function. And then you put the model that you've just run in this brackets. And then I'm getting this value and then coding it to RHO A1 and RHO A2. So doing the same thing for different groups. And the value you get is written here. So this is the autocorrelation value or parameter. Okay. This is a very simple autocorrelation, just checking how correlated two adjacent bins are. Okay, so we're just taking the log of one, compare the first bin to the second bin to the third bin to the fourth bin, and so on, and then check how correlated they are. Okay. So we got these values. Now we can create a model taking this autocorrelation into account. Right? So the model at the beginning part is identical to the model that we ran for the base model. So up to here, it's identical to the previous model. We now have this value, RHO, and this is where we put the autocorrelation parameter. So that's what we got here. Right. So we are putting this value that we got here into the model so that the model takes this autocorrelation value into account. Okay. And this is where we are putting the value that we created earlier, specifying which is the first bin. Right? Because the autocorrelation parameter can only be, you should know which one is the first bin, right? Because creating the last bin and the first bin doesn't make sense because they're not adjacent to each other. Right? So autocorrelation should be computed from the first bin and should end computing at the last bin. Right? And so that's why you need to let the model know which one is your first bin. And we've already created such a column earlier. So we can just specify which column contains that information and let the model know. Okay. So these are the additions we are including in the main model so that the model can take autocorrelation into account. You get the same warning, but this is also something we can ignore for the same reason. Okay. And this is just a model for L2 speakers. So same except for that we are taking the data from L2 speakers data and the autocorrelation value from the L2 speakers base model. Okay. Okay, so we run the model. We can check, just to double check where autocorrelation has been taken into account. Right. So if we check the autocorrelation using this function, ACF visit, we, for example, can take the base model and see to what extent the data are autocorrelated. And this is plotting the autocorrelation value. So if it's 1, it's perfectly correlated. Right? So if it's like 0, of course, it's perfectly correlated because you're looking at the identical data. If you look at like 1, the autocorrelation is high, around 0.8. Right? It gradually becomes larger if the bin becomes a bit more later. If you look at the main model, this is the model where we have taken the autocorrelation into account. So the autocorrelation value at lag 1 is significantly reduced in the model where the autocorrelation has been taken into account. Right? So you can double check that, okay, this has been the autocorrelation before it's taken into account, and if you incorporate that into the model, this value should be reduced. So that's how we can check whether it's been taken into account. We can do the same for L2 speakers. So before the autocorrelation is taken into account, it's at lag 1, the correlation is very high, also around 0.8. And if it's incorporated into the model, the autocorrelation is significantly reduced. Right. So that's all good. Okay, we can also do a quick model comparison to make sure that the model where the autocorrelation has been taken into account is better. So we can do a model comparison. They have the same structure, right? So we can only look at which one is better by checking this, like, and they see difference. Right? So in this case, the model GAN main, which with the autocorrelation parameter Aine has a lower AIC. So this one seems to be better. And the same for L2 speakers data, right? So if you do the model comparison, the main model with autocorrelation value in has a lower AIC. So that model seems to be better too. Okay, so we can now use a main model and test the difference between target and unrelated condition within each group. So we can get the summary of the model by running the usual summary function. But again, this is not really telling us when the effect occurred or how long it lasted, right? So what we do is to plot the model results. So you can do that by using the plot smooth function from the stack package. So if you do the plot smooth and then take the model that you've run with autocorrelation in, and then specify the time and condition and the color you want to use for each condition, right? And then you can get something like this, right? And then this should be plotting the your dependent variable for the conditions that you included. And the plot that you can check to test the difference is a difference plot. So what you can do is to plot the difference by calling this plot diff function, and then call the same model here, and then also across time, and then the condition that you included in the model. And now if you plot that, then you can see when the difference was significant. So that will mark the time window where the target condition was significantly different from the unrelated condition. And that will also output the time where it was significant. So the significant effect started at minus 645 milliseconds and lasted until the end of the time window. Right. For L2 speakers data, we can also do something similar. You also mark the time windows where the effect was significant, and will tell us the time when it was significant. Right. So this is what we usually look at to report or to know when the effect started or ended. Right. Okay, that's all for the GAM, we can now move on to the exercise. So in the tutorial, we compare target versus unrelated conditions in the L1 group in the code that's written here. It goes a bit right. So it's actually a bit longer than that. And this model includes random swarms, which incorporates both random intercept and random slopes. Right? And so the exercise is to modify the code so that we have a model testing the same effect, but with a different random effect structure. Right? So build a model that only includes by subject and by item random intercepts, and another model that includes by subject and by item random slope for time, but without random intercepts. Okay. Right. If you forgot how to do that, we can go back to fix the models bit, and then there is note about how to code random effects. So you can probably refer back to do this exercise. And don't run the code, that will prove you.
So Aine, for this too, you can only do this 2-level comparison and
Yes.
yeah, and by group, I guess.
Yeah.
Right. So it's not like you can, it's the same with cluster-based permutation analysis where you can't compare L1 to
Right.
L2. Right.
Right. This is also just comparing two conditions.
Two conditions. Okay.
Is there, are we still on mute?
Yeah.
Is there any of these where you can include interaction effects?
I think it was the first one.
Yes, growth curve can.
Oh yeah, right. Yeah. That's the only one.
That's the only one. Yeah, for other model, it's mainly to compare two conditions, or when two conditions started to differ. Because these models are good at when the effects started to differ. So if you are interested in difference, then you are essentially comparing when the difference between the two started to occur. So those models, so cluster-based permutation analysis and GAM and VDOTs, they all do the same similar thing in that sense. So try to detect when the effect occurs. And so that essentially compares the two conditions, right?
Okay.
Yeah, if you're interested in interaction, again, that, just like I said for the cluster-based permutation analysis, you can take the difference and then test whether the difference is different for the other condition.
Okay, yeah, that makes sense.
Any other questions from the group? Okay.
So I have
Yeah.
a original question. So what would be a good addition to this analysis to also compare, for example, the onset time of the difference between groups?
Yeah. Did you hear that, Aine?
Half.
If we wanted to compare the onset time of the effect between groups, what kind of analysis would be the most?
Right. That's the last one we are looking at. So the one looking at next, the divergence point analysis can do that.
Yeah. Okay.
And that's the only one that can do that.
Hmm. I hope we're good.
Okay, good.
Yeah, I think we're good. Yeah. I
Right,
hope.
okay, as for the other exercise, you can click the solution to get the solution. But well, it should have changed. So to model by subject and by random, sorry, by item random intercepts, you can include this to model by subject random intercept and this to model by item random intercept. And to model random slopes, you can add this by subject random slope and this by item random slope. And you can keep this, that was at the beginning of the code, because you still want to model different trends for different conditions. You expect the patterns to be different for target and arithmetic conditions in this case. Okay, any questions about the exercise? Yeah.
Sorry, can I quickly ask? So is the last thing, so the S time by condition, is that what we call the random smooth?
No, it's just that when we model the time, what the outcome does is it can fit different curves to the data, right? And when we fit the curve, we want to fit the curve separately for different conditions, and that's what this one is. We pretty much always want this when we want to fit the curve.
Okay. So but what is the random smooth then? Or is that what is essentially the random intercepts or slope? Is that what?
These two are mainly random slopes and random intercepts.
Okay.
The
Sorry.
first two, yeah.
And then what is the random smooth? Because that was
Right.
also mentioned, or is that the
Yes,
same
I
as
think I mentioned that. Yeah. Okay, so random smooth is something that you okay, but you include when you want to include random intercept or slope for the data where the curve is fitted. So in this case, when you fit the random intercept to random slope, you still want to consider the time. So how the data changes across time. So random smooth is a function that does that, and then so try to take the data trend, how it changes across time, and model the random slope for random intercept, considering that change over time.
Okay. But so sorry, in the tutorial or the S time by condition, the one that we have to keep, that is not the random smooth. That is just a random.
Yeah, that is just a smooth. Yes.
Oh,
so
that
this
is the
just
smooth.
Yeah.
Oh, okay. I think I got it. Thank you.
It's a complicated.
Yeah.
I don't remember but that had the regnet, but
Okay, thank you. I'll
probably,
study
but
more.
yes. Sorry.
Yeah, so Aine, the second one here, time subject, that's like the random intercept is subject and slope is time, right? Kind of. Like the random or
yes. Sorry,
by
random
subject,
slope.
yeah. By subject random slope of time per subject, right?
Random slope
No.
by subject for condition, because we have the condition here.
Right.
And time is always there because we have that. I mean, we want to model it with time together. Like it's not like average across time, but rather we want to
Right.
have the
Okay.
data.
Okay. Yeah, I think that's
process.
where. So like if we were to put this in that LME type of thing, then the second one is like a condition slope by subject.
Right.
Across
Plus
time.
yeah, so this one includes both the intercept and slope. So if we were
Right.
to put this one in LME, right, I'm probably write it in the chat. So if we are to put this in LME, it will be something like
Oh, yeah, thanks.
something like this.
Right.
Like,
Yeah. Okay. Yeah. Yeah. Yeah, that's what I was thinking. But then what's the thing before that, time by condition? So is that just like 1 plus one, like what do you call this bar and then time?
This one is not random slope or random intercept, but rather just saying I want to fit the model for separately for each condition.
Ah, okay. I see. Okay. Yeah, I think I was confused with just that one. I get that the second and the third is like a random slope for subject and item. Yeah, okay.
Yeah, this one's mostly for modeling the curves. Right? The GAM also fits a curve to the data. And when we do the curve fitting, we want to tell the model that we want to fit the curve separately for condition. And this is the bit that's telling the model.
I see. Okay. All right. Any other
Anything-
questions? Yeah. No? Okay. I think we can go to the solution.
Okay, I think we already took the solution, right? So yeah, these are things that we should have changed. Okay, shall we then go to the last tutorial, the divergence point analysis? Good, then I'll close this and open the divergence point tutorial. So what you need to run is this.
Yep, I think it's all good on this side. Yeah.
Okay, yeah, this one should be fixed to open. Right, okay, then it's the final tutorial. So the divergence point analysis is to test when or how early the effect started for one condition compared to the other. So you can test the onset of an effect and whether the onset was different between the two conditions. So here again the packages that you need to run this analysis, and you already know this, so you skip this bit. We're going to use the same data set, but this time I called it, I used the 20 millisecond bin instead of 15 millisecond bin, so it's a slightly smaller time bin. Because we are interested in the onset, so it's bit more detail. You can get a bit more detailed result if your bin is smaller compared to when the bin is larger. So I made the bin slightly smaller. So everything else is still the same. So it's just that the bin, one bin now contains 20 millisecond data instead of 15 millisecond data. Okay, so these are the description of data. Again, identical to what we've seen in previous tutorials. So in this tutorial, divergence point analysis tests the divergence between the two conditions. So in this case, we take again the target and unrelated conditions to compare these two conditions. So when the target object started attracting more X compared to the unrelated object. Okay. So if you look at the summary, we get something similar. So we have the subject, trial number being time, the count, that's dependent variable, condition, time, and language group. Okay. So we can plot the data again. So we are trying to plot the time course data. And for now, we are saving the plot as P1 because we want to plot the other results to this plot data. Okay, so we are plotting this. This is all the plotting function, and we're just assigning this plot to P1. if we print the plot, what we plotted is something like this. So this is just a standard time course graph plotting the fixation proportion to the target and unrelated conditions in L1 unrelated speakers. Okay. And we can add the divergence points to this graph vector. Okay, so that's the data. We can now prepare the data for the divergence point analysis. So we first select the time window for the analysis. Okay, and the time window should be large enough to capture divergence point. So there should be a time point where these two conditions that you include in the data start to differ. If there's no difference between these conditions, the model won't run. Because the model is testing when the effect started to occur. So if there's no effect, then you can't really detect the divergence point. Right? So the window should be large enough so that there is a divergence point in the time window. But it should also not include the time bins with very few observations. Like if you have lots of data exclusions for a specific time bin, maybe because he just started showing the pictures or the sentence just started or something. Right? If that's the case, we are using a t-test as a base test for this analysis. So t-test won't run if you don't have, for example, many observations. So because it could be that all your data is 0, all your data is 1. Right? In that case, the data t-test won't really work. So in our case, we are including a time from minus 800 milliseconds. So that's 200 milliseconds after the pictures were shown. So that should be when people start moving their eyes. Okay, so that's the starting point I'm including in this data. The commands below that we have here, we also create what is called a stratification variable. And data resampling will be done based on this variable. So in this case, when we want to shuffle the data, bootstrap the data, we want to do that within subject, within condition, and time. Right? So we don't shuffle data across different subject or across different conditions. Right? We want to respect this structure and shuffle within subject and condition time. We obviously don't want to shuffle different time. So we want to respect that structure. So to do that, we create that stratification variable that is called strata bus. We're just pasting all the values, subject, condition, time all together. So what we get, it looks like this. So if you just look at the head of the data set, this is the strata bus that we just created. So this is just pasting the subject ID here and the condition tag, and then the time, so minus 800, right? So if we randomize the data within this variable, then we are randomizing within subject, within condition, and within the time window, right? So that's why we created this variable. Okay, so that's the preparation. Now we can define a bootstrap function. And this is a very long function, so we look at this function bit by bit. Because when you run this, what you need to do is actually to run this. And if you run this function, it will do everything that's in here. But you want to understand what this function is doing. Right? So let us look at this one by one. Right? So instead of like looking at this as a chunk, we will go through what these lines are doing. Okay. So the first step that we have here is to create a by subject summary. Okay, so this is like what you do when you do a t-test, right? So you first create the by subject summary and run the by subject analysis, right? So the first bit is just creating the group data by subject, condition, time, and language group, and then summarize the data. So this is just creating a by subject summary of the dependent variable. Right. Right, and then that's the data that we get here. In this case, I'm getting the log transform fixation proportion as a dependent variable here. Okay. So we've got the by subject summary, so we can just run a t-test. Right, so you know how to run a t-test, I think. So you can just subset the data for A1 group or A2 group separately and group by time, because we want to run t-test in every time window first. Right, so we first group the data by time, and then run t-test, testing the log fixation proportion that we have here, predicted by condition, right? And then what we're getting here is just a t-value from the t-test and putting that into the variable t, right? So if we run this, we will get the t-value for each time window using A1 speakers data. Right, so this is just running t-test in each time window, and so each time b, rather, and then store the t-value that we got from the t-test for each time b. Now, based on this t-test, we can get when the effect started to become significant, right? So if you remember in the divergence point analysis, at this point, what we want to do is to take the first time being where the effect was significant, right? When the effect was significant for many consecutive time beings, right? So if we first run this, what we get is the true or false value, whether this t-value is significant or not. You are using the threshold 1.96. So if we have a t-value that's larger than this value, then we put true, and if not, we put false. Right. So if it's significant effect, we put true. If it's not, then we put false. Right. So this starts from the first time being. So the first one corresponds to this time being, and the second one corresponds to this time being, and so on. Right. So we have false, 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 and then at some point this becomes true. This is the first time being that the effect was significant, and then that keeps being true, right? So we get this, and then we can just create an empty vector that we will use later. So this is just creating empty thing, okay? And now we run a for loop to get the first being of the 10 consecutive truths, right? So in this case, what we want is what is this value, right? So in this case, you have true. So when you have 10 truths, 10 consecutive truths, we get the first true, right? So if we run this, we know, okay, it's the 9th being where the true first appeared, right? Of the first of the 10 consecutive beings. Okay. Yes, that's what we are doing when we run this function. And we are doing that for both L1 and L2 speakers, so some calls are repeated. Okay, so just to recap, we first created the by subject summary, and then we run a t-test. This is for L1 speakers, t-test, L2 speakers, t-test. And then we get the true false vector specifying whether the test is significant or not. And we have that for L1 speakers and L2 speakers. And we created an empty thing to put the values later, right? And then here is the for loop again to get the first true of the 10 consecutive truths, right? And then we are putting this in to these empty vectors that we created, G1 for L1 speakers and G2 for L2 speakers. And we can also create a difference by just doing the this onset of the group 2 minus the onset of group 1, right?
And then we ask a quick question.
Sure.
Is it arbitrary that you set the earliest run of 10 sequential truths?
Right. Yeah. So that is your choice. So you need to decide that on your own. So if I set it 10 here, because my bin is 20 millisecond rush. So if I set it 10, I want my effect to last at least 200 milliseconds to be reliable. Right? So if you think your effect is much shorter, if you think your effect actually doesn't last that long, then it might make more sense to make the threshold a bit smaller. But if you set it too small, it will also detect some noise. So you might actually get large variability or standard deviation in your data or confidence interval in your data. So you don't also want to make it too easy to lose.
Okay.
A short question. Is these 200 milliseconds, is that motivated by the observation that it takes around 200 milliseconds to generate a saccade?
Actually, no, but rather the fixation seems to last somewhere around 200 milliseconds on average. So if you think when you look at something, you typically spend there for 200 milliseconds. That's more the time facing that. Yeah, but sometimes you look at something and move your eyes quickly to something else, right? So if you think you effectively fix that and a process like that, then it may make more sense to, make the space a little bit tighter.
Great.
Yeah. Okay. Right. So that's what we are doing when we run this function. Right. So if we just put the data, we can just run everything that we've just looked at in this function. Okay. So we define this function like that. So let's move on to the next topic. All right. Now we can run the bootstrap now that we have the bootstrapping function. So for this analysis, we also bootstrap the data, so shuffle the data many times. And the usual number that's good is typically 1,000 to 2,000. Again, the larger, the better, but the larger, the more time you need to run the analysis. Right. So somewhere around 10,000, sorry, 1,000 to 2,000 would be good. Here we're only running it to, we are setting it to 100 so that the tutorial can be opened quickly. Right. So you need to change this number to a larger value when you apply this analysis to your own data. Okay, so this is the actual function to run the bootstrapping. So we are using the function called boot from the boot package. And to run this, you will specify the data set you are using to run this analysis. And then this function is the one that we just created. So when we created the function, we specified the function and call this function boot L1, L2. Right, so this is what we are putting here. Okay. So this is a bootstrap function that you just created. And then this is the stratification variable that we created when we prepared the data. So this is this value. Right. So we want to shuffle the data. We want to respect this structure in the data. So that's what we have here. And then this is the number of iteration. That's what we specified above. Right. So we can put all this information in and then just run this. Right. And then you can get the results by just running this bit. Right. And then what you get is this. So at this point you have like T1, T2, T3, and what is called original and what is called bias and what is called standard. Right. So these numbers can't really be straightforwardly interpreted at this stage. So we convert this number to compare these numbers to our data. So we can first get the onset from the original data from this. So it's 17, 9, and 26. And this is the onset from the original data. So if you run lots of t-test, what is the first data point what is the first time being where the effect becomes significant, right? And bootstrap onset, so if we shuffle the data many times, we get the divergence point every time we shuffle the data, right? And these are stored here. So in this data set and T is where these onsets are stored. So we have now lots of onsets for these three things. So for L1 onset, L2 onset, and difference between the two groups, right? Now, again, these numbers don't really make sense if you just look at it. So we convert the mean onset times to milliseconds. So these are not milliseconds. So we convert these to milliseconds using the command below. Okay. So we first subtract 1 because the first timestamp has an index of 1, but it actually should be 0. The starting point should be 0. So we subtract 1. And then we multiplied it by 20 because our bean was 20 milliseconds. So each bean contained 20 millisecond data. So this number varies depending on your bean size. If you use 50 millisecond bean data, you need to change this number to 50. And then we finally subtract 800 because our time window started at minus 800 milliseconds. If your time window started at 0, then you don't need to add this final minus 800. Okay. So that's the adjustment that we're doing. So here, so we first subtract 1 multiplied by the bin size, and then the starting point of the time window. Okay. So if we run this, one thing that I say is this T, the second bit is when where the A1 data is stored, and then the third one is where the A2 data is stored. This is actually set here. So because we specified that here. So the first one we put is a difference between the two groups, and the second one is the onset. For the first, so the group 1, so that's A1 group, and the third here is the value for A2 group. Right. So that corresponds to, I think here, this will appear as T1, and this will appear as T2, this will appear as T3. Right. So that's what we are getting at this stage. Yeah, so if you want to get the A1 onset time, you would need to use this value. And if you want to get the A2 speakers onset, you get this value, right? And then do this adjustment, and then you get these values, right? And now these are in milliseconds. So the onset in A1 speakers were minus 532, and then A1 is minus 3. Okay. Now, what this means, but divergence point analysis, you can also compute the confidence interval, right? So that's what we'll do next. So this boot package has a couple of functions for computing confidence intervals, but the main one is the boot.ci, and that's what we are going to use in tutorial 2. Okay. So to do that, we call this boot.ci function, and then put the bootstrap results. And then this time we want to get the first index. So the first one was a difference between the two groups. Okay. This again corresponds to what we specified here. So the first one was the onset difference between the two groups. Okay, so we can get that here, right? So we get the index 1. Okay. And this is the specified its percentile. So we want to find the 2.5 percentile and 97.5 percentile, right, to compute the confidence interval. That's what pass means. So we run this, and then the values we get 15 and 59, these are not in milliseconds. So again, we want to convert these values into milliseconds. So we just get the same value and then just multiply it by 20, right? Because again, our bin contained 20 milliseconds data. So if you multiply it by 20, we get these values. And this is just these values multiplied by 20, and that's what we get here, right? We can also compute the confidence intervals in milliseconds for the divergence point themselves. And so for the A1 speaker data, for example, we now get the second index. So we change the index to 2. And then the rest is the same, but we made some adjustment. Because this is different, so it doesn't really matter. You don't need to make such adjustment just to make the difference, just to make the adjustment for the bin size. But this time is relative to the target or the onset, right? So we need to make that adjustment. The same for A2 speakers. We now take the index 3 to get the A2 group's divergence point, right? And now if we do that, we can get the confidence interval for A1 speakers divergence point and A2 speakers divergence point here. Okay. So now that we got the results, we can plot the results on the plot that we created earlier. So we had the plot called P1, and this is how we add the bootstrapped divergence point, the mean, and the confidence interval. Okay, so to get the mean, we're using this jump point function to get the mean. So this is the value that we had from the earlier bit. So we have bootstrap results here, and we're taking a second index because this is for A1 speakers data, right? And then this is the same adjustment that we made earlier, right? So we get the mean of this, and then put that on the x-axis, right? And for the error bar, you can now put the confidence interval information here, right? So the minimum value here should be the 2.5 percentile. So now we get the A1 speakers data by specifying index equal to, and the percentile 4 corresponds to the 2.5 point, and the percentile 5 corresponds to 97.5 percentile, right? So it's the minimum side and the maximum side, right? And so if we plot this, for example, for A1 speakers data, this zone point here is plotting the mean divergence point for A1 speakers. So this is the mean when the target condition started to be different from the unrelated condition. And then this is the confidence interval, right? So this is the minimum point and the maximum point, right? And the same for A2 speakers data. The mean was just around the target toward onset, and then the confidence interval is much larger in A2 speakers data. Right? So that kind of actually includes the data point as well. Okay, so that's how you plot the results onto the fixation proportion graph. Okay, here's a small quiz. So based on the results that we just got, so based on what we have here, which of the following statements can we say select all that apply? So I'll give you a few minutes to work on this.
Aine, just a quick question since the first part. So this the index 2 and 3, I get that it's you know, for L1 and L2, but index 1 is the difference between L1 and L2?
Yeah.
Okay. Okay. But why was
Yeah.
it 300 to 1000 or what is it when you
Sorry,
convert
where does the value come from?
onset difference, like when you give us the when you computed it to milliseconds? Oh, right. So here, yeah, this one, does that mean that the difference between L1 and L2 groups, yeah, what does that mean there with 300 to 1?
Right. No, so this is the confidence interval. So the confidence interval of the difference. So this percent here, yeah, is taking the confidence interval.
Oh, so the confidence interval, the difference is from 300 to
Yeah.
1180. Okay. I see. Okay. Sorry, thanks.
Yeah. Okay.
And maybe can you go to the quiz, Aine, so we can see it?
Oh, yes. Right. Sorry.
Okay.
So it should show together with the graph.
Okay, sorry, Aine, our screen turned off again because
Oh,
they're trying to save energy. Oh, here, can you hear me?
I can hear you.
Okay, can you guys hear from mine? And then you can turn it off. Yeah. Okay, so I think we all said 1, 2, and 4.
Okay.
Yeah, except
Okay.
everything except for 3.
1 to 4. So I just check it so I don't forget. Right, so let's look at it one by one. So the first one was the L1 group started looking preferentially at the target before the acoustic onset of the target was. So we are looking at the L1 speaker's data here. Acoustic onset of the target was at the point 0, right? And the confidence intervals don't overlap with the target or the onset, right? So we can conclude based on this that the onset, the divergence started significantly earlier than the target or the onset. Okay. The second one was A1 group started looking preferentially at the target around 500 milliseconds before the acoustic onset of the target was. And that's exactly where the divergence point fell, and the confidence interval also overlapped with the minus 500. And so we can also say this. The third point, the two groups started looking preferentially at the target before the target was onset. Target word could be processed, considering that it takes around 200 milliseconds to make eye movements in response to spoken stimulus. So if we take the 200 millisecond lag into account, so that should be somewhere around here, right? So the mean is before the 200 millisecond point, but the confidence interval includes that 200 millisecond point, right? So we can't say that the L2 speaker's divergence point was significantly earlier than the 200 millisecond time point. Okay, the last one, the A1 group were quicker to start looking at the preferentially. So looking preferentially at the target than A2 group. We can also say this because when we compare the confidence intervals in A1 and A2 speakers, they don't overlap with each other. Right? So we can conclude, we can say the last point too. So if we should submit this, that should all be correct. Right. So we can use a confidence interval to compare whether the divergence point in one group is significantly different in another group or significantly different from a certain point in time, like target or onset. Right. So you can do this, but sometimes you might need a p-value. Right? So that's what we will do next. Maybe some reviewer says that I don't trust the result unless we have a p-value, or maybe your result is not so straightforward. There's some small overlap in the confidence interval, and we want to quantify that using a number, for example. Right. So let's do that next. So to compute a p-value, what we do is to create a null distribution and compare what we get against the null distribution. Okay. And so what we do to get the null distribution is to run some similar bootstrap function that we ran before, but there's some small change we need to do to the previous function. Okay. So the first bit is similar up to this point. So we first want to create a bisubject of this data, but here, what we're doing here is to randomly assign group levels. Right? So when we want to compare L1 versus L2 speakers data, and if we shuffle the group randomly, right? So sometimes L1 speakers data is assigned to L1 speakers, sometimes it's assigned to L2 speakers, and sometimes L2 speakers data is assigned to L1 speakers, right? So if you randomly shuffle that many times, you will get the null distribution, right? Because the conditions are randomly shuffled. Right? So it's not respecting the original group assignment anymore, right? So we will randomly assign the group levels here to get null distribution. Okay. And again, we do that many times so that the distribution will be closer to the null distribution. The other thing is the same. So this is the same. We just create a different variable that we need and the t-test here for different groups. And then the rest is also the same. So we take the things that are significant, right? In this case, we only need the difference, right? And we are interested in because this difference should be, the distribution of this should be centered roughly around 0, and they should be roughly normally distributed, right? So we can run this bootstrap just like we did before. This time what you get should be the should be null distribution, right? And what we do to get the p-value is to compare the original model against this null distribution model, right? So here what we are doing is to get the distribution from this null distribution model, and then get the distribution from the original model, right? And then test how many of the data points from the null distribution is larger than the original distribution. Right? If the null distribution is larger than the difference in null distribution is larger than the original model, then the original difference is likely to be closer to zero, very small, right? Because null distribution shouldn't show a big difference between the groups, right? So, yeah, that's how we get the p-value. So it's not like how you get the p-values in usual t-test. Right? This is computing the proportion of the p-values from null distribution, which were larger than the original distribution. Right? So if many values from null distribution is larger than the original p-value, then the difference in original p-value difference in the original data should be very small. Right? So we get here, so none of the null distribution data was larger than the original t-value. But this is probably not very accurate because we only resampled the data 100 times, right? So in the actual analysis, you should resample the data many more times. At least you want to set the number to 1,000. So this part, the p-value is not likely to be accurate, just to mention, but the computation is just the same. You just need to change the number of resampling for your data. Okay. Okay, so to report the results,
Sorry,
yeah.
one quick question. Yeah.
And then as long as the result of that is like 5, in this case 5 or lower, then you're good, right? Or if you do it, is that how?
Yeah, just like p-value, if it's more than 0.05, you conclude that. Yeah,
okay.
that should definitely match whether the confidence interval overlap or not.
Okay.
Yeah, so when reporting the results, you will report the mean, or something like this. So the mean difference in divergence point between these groups was this. This is probably not the exact same number because every time you run the analysis, you get slightly different number. So this is probably not the exact number, but what you get, what you report is the mean difference between the two groups and the confidence interval when you want to report the difference. If you just want to report the divergence point for one of the groups, you will report the mean divergence point here, and then the confidence interval together with that. Okay. Okay, then we can finish off with the exercise. Okay, sorry, this is a function, so it's a bit complicated stuff. But so we define the bootstrap function as using this code below, right? So let's say we now want to modify this code to perform t-tests using a mean fixation proportion as a dependent variable. So we have a mean fixation proportion here, but what we use is actually the log fix here, right? So we now decided that we actually want to use the mean fixation as a dependent variable. And we also decided to change the significance threshold to the t-value being smaller than 2, right? So that's what we want to change second. And finally, we want to consider an effect that lasted for 300 milliseconds instead of 200 milliseconds as significant. And just to note that the bin size is 20 milliseconds. Okay, so I'd like you to modify the code to do all these three.
I think some of us are done, Aine. But I think, yeah, we're good.
Sorry, I was unmuted. Okay, yeah, I just realized that you have exercise 2 as well, so you can probably go ahead with that. So exercise 2, we run the code below this code to get the confidence intervals for the A1 group, right? So if we had to use a time window from minus 500 milliseconds to 200 milliseconds, and if each being contained 15 millisecond data, then how should we change the code? We can probably do the exercise 2 if you've done exercise 1 already.
Okay. All right, I think we went through both together.
Okay, good. Then let's look at the solution. Okay, so for exercise 1, I usually change the following things. Okay, so for the t-test, because now you want to use the mean fixation as your dependent variable, your dependent variable in t-test now should be mean fixation instead of the log fix. And then you need to change the threshold to smaller than 2. So maybe let me go back to the previous bit. So this is when you specify the threshold. So in the previous model, we specified if t value is larger than 1.96, we treat it as a significant effect. But you now want to change it to t value smaller than 2. So that's when you expect the unrelated condition to be fixated more than the target condition, right? And then when the effect goes opposite, you want to specify the t value should be smaller than 2, and you want to change that for both groups. And then last point was that you now want to consider the effect that lasted at least 300 milliseconds instead of 200 milliseconds as significant. And that's when you specify using the for loop. Right? So for the for loop, you want to change the number here. So if it's 10, we have 10 bins multiplied by 20 milliseconds. So we now think that, okay, if the effect lasts at least 200 milliseconds, we want to take the first bin, right? If you instead make it to 300 milliseconds, we put 15 into these numbers instead, right? And this number here is just this number minus 1, because this is now, this is taking from the first bin to the 10th bin, right? So if we, for example, get the first to the 10th bin, this I value is 1. So if we wanted to put 10, then it's already 1. So this number should be this number minus 1. So what we get is 15 to this number, because 15 multiplied by 20 is 300, right? And so we put 15 here, and then number here we put 15 minus 1, so we put 15, 14 here, right? Right, and then that's the calculation we do. Okay. Okay, for exercise 2, you should have changed the following. So we want to change the bin size from 20 to 50 and change the time adjustments to minus 500, right? Because the first time bin now is 500 milliseconds. So if we go back here, this number should be now changed to minus 500 instead of minus 800, because this should be the first time bin. And what was the thing? All right, the time bin should be changed to 50. So instead of using 20 here, if your bin size is 50 milliseconds, then you should change this number to 50. Right, so that's the bin solution. You should get 50 here and then 500 here. Okay. Okay, that's all. Any questions?
Any questions? Final questions?
Yeah. One. So when we look at the confidence interval for the L2 group, we see that it spans a much larger range. Does this allow us to say something about the uncertainty of the effect?
Yes, yeah. I think you often find the speaker data have more variability compared to the speaker data. I mean, I know what many of you do bilingual research, so that's probably typically what we found. We can't statistically compare the distribution. So we can't say this distribution was significantly, like the data is more significantly more variable compared to the speaker's data, but we can numerically or by visual inspection say that the variability was much higher than the speaker.
Okay, so but just by visual inspection, it is statistically
Right.
not valid to say.
Yeah, statistically we can say these confidence intervals are larger in the speakers than in the speakers.
All right, any other final questions? Okay, so I think it's a good time to stop here. So let's give another round of applause to Aine for doing everything. Thank you so much. I think this was, very helpful for a lot of us here. And we will, if you missed some things, we will post it on our YouTube channel in Aqua. And yeah, thank you, Aine, again for all your hard work in creating all these tutorials. Yeah, it was super nice. And
I sent Maki the slides from yesterday, so he could distribute the slides.
I will upload everything on the Aqua page. So if you guys want to have the slides from yesterday too. All right, so I'm gonna stop recording now.